get honor to speak this conference. So let's take irrational number x and consider its continuous fraction expansion, which means it's possible to develop
in this way, x equal to in this way. Okay, I write this in this way. This is a standard notation. This is a continued fraction expansion of the irrational number x. Okay, so each ai is it of course depends on x, and it's a positive integer. Okay, so I don't understand the behavior of these continued fraction digits as I goes to infinity. Okay, this is the question I want to address, and this question has been considered extensively since the time of Gauss, Carl Friedrich Gauss, and the behavior of the digits is very interesting. Well, I will, yeah, both. I will talk about it later. Yeah, for typical x. Okay. Yeah. Okay. So, for example, let's take golden mean. Sorry, golden mean. Okay. So its continued fraction expansion is only one appears in the expansion. Okay. So it's known that the continued fraction expansion is periodic if and only if the irrational number x is a solution of the quadratic equations with integer coefficients. Okay. There is another example I discovered in the internet. So let's take Champanon constant. That is irrational number obtained by aligning all the positive integers in the increasing order. Okay. It has a continued fraction expansion in this way. So it begins with 8, 9, and 1. And next, we have a very large number, which is okay. Suddenly, we have a large number. And after that, relatively, we have relatively small numbers. And the next one, this comes, here comes sorry? Okay. Sorry. Okay. 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 So let's take a Champanon constant and consider its continued fraction expansion. Then you have here, here comes a very large integer which has 166 digits. What's the question? I don't know. I know it's a rational number anyway. Yes. Yeah, I want to give some. Okay. So anyway, I want to understand the. Okay. So anyway, I want to understand the behavior of the continuous fraction digits as I goes to infinity. But I'm interested in the metric theory of continuous fractions, which means, in particular, I'm interested in this asymptotic behavior for typical irrational numbers in the sense of the Lebesgue measure. So I want to understand the behavior for Lebesgue almost every irrational numbers. Okay. So in this direction, there is a famous result by Hinchin, which says the following theorem of let's take arithmetic function phi. That is positive such that psi is defined on positive integers. Yeah. Okay. And I assume the following conditions, following upper bound conditions. So there exists a constant and rho such that psi n is bounded from above by c times n 1 minus rho. Okay. For any n. For any n. Okay. Then we have the following 1 minus rho. Okay. Then we have the following formula for the limit of as n goes to infinity of this sum with k from 1 to n of psi a k. The case digit of the continuous fraction expansion of the irrational number x. This exists. It's equal to the following infinite series. So this holds for any for can you see this? Okay. For for Lebesgue almost irrational numbers. Okay. So that's a classical theorem of hinching concerning the typical asymptotics of the continuous fraction digit. Although Hinchin did not use the ergodic theory, the given function, then this equality holds for Lebesgue almost every irrational numbers. Okay. And Hinchin did not use for this proof the ergodic theory, but now this is a consequence of Birkhoff ergodic theorem applied to the Gauss map that is defined by I write by T, which maps 0, 1 to 0, 1. Which sends the point x to 1 over x minus the integer part of 1 over x. Okay. So this is a uniformly expanding interval maps with countably many branches. This is 0, 1, and the rightmost branch is this. In this way, it has infinitely many branches. Okay. Then so let's take irrational number x and consider its continuous fraction expansion. Then its ith digit aix is equal to some integer k. If and only if t I minus 1 x belongs to this interval. So this means the iterates of the Gauss map generates a continuous fraction expansion. So considering the Gauss map, convert the problem of the asymptotics of the continuous fraction digits to the problem of the dynamics of the Gauss map. And this measure, this map, the Gauss map leaves invariant the absolute continuous invariant measures. So that is d mu g 1 plus x over sorry. So this is called the Gauss measure. Which is, of course, absolutely continuous with respect to the Lebesgue measure. And that is invariant under the Gauss map. And it's ergodic. Okay. So there is for the ergodic theory to work for the Gauss map. For the observable, I take use hinging formula. I take the following observables. Let's take phi, the given psi in hinging theorem, composed with the first digit function. Okay. Okay. I regard the first digit as a function of x. Okay. So then this number is using this relation. This number is equal to, in fact, equal to t. There's this this relation. So the sum in Hinchin's formula it's nothing but the Birkhoff sum of the function phi composed with the first digit. So applying the Birkhoff-Ergodic theorem to the Gauss measure and this observable, we get the Hinchin's theorem. Okay. So that's a proof of the Hinchin theorem using the Birkhoff-Ergodic theorem. But here there is one important assumption on the function psi. It's not allowed to grow very fast. So I assumed phi n is bounded from above in this way. So the identity function psi n equal to n, this is not allowed. This function obviously does not satisfy this upper bound. However, taking phi n to equal to n gives you a very important quantity because yeah, right. This condition implies the integrability. Yeah. If you take this function, it's not integrable anymore. So let's take phi n equal to n. Then this gives you the sum of the digits up to time n. So dividing by n, you get the arithmetic mean of the continued fraction digits. And it's of course interesting to know the asymptotics of the continued of this arithmetic mean. as n goes to infinity. And there is a fact that this arithmetic mean diverges to infinity. For Lebesgue almost every irrational numbers. Okay. This is a classical fact. This is a bit fact, maybe, but still it makes sense it makes sense to analyze how fast this divergence takes place. Okay, so more precisely, let me give you the setting of my problem. So let's take number alpha, positive number alpha. Let alpha be positive. Then I would like to ask how fast the Lebesgue measure of the set of irrational numbers which the arithmetic mean is smaller than or equal to alpha. This goes to 0, how fast as n goes to. This is my main question. And particularly interesting is the exponential case. So is this speed exponential? And if that's the case, I want to know the rate, exponential rate. And besides that, I want to know that the dependence of the exponential rate on the parameter alpha. Okay, I'm going to give rather complete answers for these questions. Okay. So the main theorem. Let's put here. So let's take a function psi defined on the set of positive integers and taking values, taking real values. I don't assume I don't assume its value is positive. Okay. And assume the following two conditions. First, the limit if as n goes to infinity of psi n is infinite. Okay. And one more condition I request is this psi composed with the first digit function, not integrable, Lebesgue integrable. So infinity. Okay. That's the assumption. Then the limit first. Okay, so this exists, but it can be negative infinite. So when it is when the limit is a finite number, there exists a number alpha 1 such that J alpha is finite if and only if alpha is bigger than or equal to alpha 1. Later, I will give you the definition of alpha 1, more information on this number. Okay, the last statement. This value is positive, bigger than 0, and can be infinite. And decreases to 0 as alpha goes to infinity. Psi. Sorry. Good remark. Here. Okay, so, thank you. Here. Yeah, very important. Thank you. I made a correction here. Okay. It's a Birkhoff sum of phi composed with the first digit function, written in this way. Okay. Sorry? Here? Okay. The set of X here. Yeah, sorry for my writing. So this function is convex. And so never becomes 0. So here, this is important. That's a statement of the theorem. So I will give you the drawings of the function J alpha here. So here alpha 1, and J alpha is finite if and only if alpha is bigger than alpha 1. And it decays to 0 as alpha goes to infinity, like this, and monotonically. Monotonically decreasing, and it goes to 0 as alpha goes to infinity. Okay. And for alpha less than alpha 1, it takes plus infinity. Okay. Okay. So this is a figure of the function J alpha. So roughly speaking, the function J alpha gives you the exponential rate of the divergence. Yeah, right. Yeah, right. Yeah, it's a convex function and strictly decreasing to 0 as infinite. Yeah, right. It's infinite. Yeah, it doesn't look like a convex. Yeah, okay. So, okay. Yeah, you are right. It's finite for every alpha bigger than. Yeah, it's finite. Yeah. So this number gives you. What do you mean? This one? No meaning. So let's see. This is a graph. So here is a jump. Okay. So the value J alpha determines the divergence rate of the level set. Okay. Then I will give you more information on alpha 1 and so I need some notation. MT is the is the set of T. T is a Gauss map, and T invariant Borel probability measures. And for each mu, H mu is the entropy with respect to the Gauss map T. Okay. H mu is the entropy with respect to the map T, Gauss map T, and that can be infinite in this context. So define its Lyapunov exponent chi mu. That's the integral of the log of the derivative of the Gauss map T. So this can be also it's strictly positive, but it can be infinite as well. Okay. So this is a Lyapunov exponent. Okay. Then this function, it's called a rate function. So I will give you the definition of the J alpha. J, so minus J alpha. That's a negative number. It's defined to be the supprimum of the entropy minus the Lyapunov exponent of the measure mu, where the supprimum range is over all mu in the set of T invariant probability measures with finite Lyapunov exponent. Mu is finite. And the integral of the phi psi composed with the first digit function against mu. This belongs to the interval of alpha minus epsilon, alpha plus epsilon. So first I take the supprimum of P minus the Lyapunov exponent over all invariant measures mu with finite Lyapunov exponent and with integral of this function roughly equal to alpha. And finally, I take a limit, let epsilon goes to 0. This definition of the J alpha called the rate function in the main theorem. So what's the definition of alpha 1? Alpha 1, it's a supprimum infimum of the integral of the psi composed with the first digit function. The infimum ranges over all mu T invariant with finite Lyapunov exponent and so okay, so this is a definition. If so we have to care about the Lyapunov exponent. The Lyapunov exponent is finite, then automatically the entropy is finite. So this difference makes sense for these class of measures. Okay, so now we have defined the two numbers in the main theorem. So that gives you the complete statement of the main theorem. Fine. Okay. So for the rest of my talk, let me give you. I will talk about some the structure of the proof of. So I forgot to mention that in the main theorem. In the main theorem, take phi psi n equal to n covered in theorem. So taking that way gives you the arithmetic mean of continuous fraction digits. So the main theorem gives you the divergence, exponential divergence rate, arithmetic mean of continuous fraction expansion. So main theorem fairly completely answers my initial set of questions. Okay, that's okay. So the proof of the theorem that splits into two parts. So the first part is to show the limit theorem in a general context called the large division principle. So let's take a function psi defined on the set of positive with real value functions. I don't assume the positivity of these functions. Okay. Then for any Borel set gamma Borel subset of R, we have the following lower and upper bounds. So lower bounds. So limit if n goes to infinity of this bigger than sorry. This average belongs to gamma, the interior of gamma. Okay. This number is bounded from below by some the infimum of the I alpha. I will later give you the definition of alpha. Alpha belongs to the interior of gamma. first proved by Denka and Kabruchko for a limited class of functions, including those. But in the result, boundedness is crucial. So psi has to be a bounded function. In their result, boundedness is crucial. While in this proposition, I don't assume anything on the function psi to cover n equal to n, the most interesting case. And here I want to emphasize that in this proposition, I don't assume the existence of ergodic averages. Okay. No assumption on function psi. Okay. So in fact, in the formulation of the large division by Donskoy and Baladan, they don't assume the existence of average values a priori. So it makes perfect sense to consider large deviation principle regardless of average values. So through this work and some related recent ones, I'm under the impression that beyond the uniform hyperbolicity, the large division principle can be a more universal limit theorem than the law of large numbers. That's my recent impression. Okay, this is one of the main ingredients for the proof of the main theorem. So lastly, I will mention the second ingredient that was essentially done by other group of people that I'd like to mention. So based on proposition 1, so it remains to show the following. Take a function psi. Real valued function psi on the set of integers and assume the primitive is infinite. And psi composed with A1 is not integrable. Then alpha, it never becomes 0. And it goes to 0 monotonically as alpha goes to infinity. Okay. The rest of the properties of the function J alpha is more or less obvious from its definitions. So it remains to show these two properties. And this part, it has to be strictly positive for any alpha. I use the following. So the argument is by contradiction, assuming that J alpha vanishes at some point. So the easy observation is that J alpha 0 equal to 0. This is equivalent to there exists some sequence in the set of the invariant Borel probability measures is whose entropy minus the Laplace exponent, this goes to 0 as n goes to e, and the integral of a1, sorry, psi composed with a1. This goes to alpha 0 as n goes to infinity. So this was the existence of such a sequence. So by contradiction, if I assume J vanishes at some point alpha 0, then there must exist some sequence. So to proceed, I have to analyze the dependence of the entropy and the Laplace exponent on measures. In this setting, the minus, so this part, the minus of the Laplace exponent is upper Riemann continuous as a function of measures. However, the entropy is not so. It's not the entropy map is not upper semi-continuous. So this means that to analyze the dependence of this quantity on measures, it's not a good idea to consider entropy and Laplace exponent separately. Okay. And this kind of problem it was already present in the multifractal analysis of the interval maps with countably many branches. So to overcome the lack of upper semi continuity of the Laplace exponent, I have used the following known results. That's done by a group of people. One, Jordan, Liao, Rams in 2014. So their lemma implies the following in our context. So let's take a sequence in the set of gas measure invariant Borel probability measures with assume its Laplace exponent is uniformly bounded. When converges in the Weikster topology to measure mu, that's automatically belongs to that's automatically the invariant. Okay. We under these assumptions, and the entropy of mu n divided by its Laplace exponent converges to 1 as n goes to infinity. Then we have the following. Then we have this type of limited form of upper semi-continuity of entropy divided by Laplace exponent. So namely entropy divided so this limit soup is 1. So namely entropy of mu divided by its Laplace exponent is equal to 1. Okay. I use this kind of limited form of upper semi-continuity in a crucial way to deduce the rate function does not vanish at any point. That's all. Thank you. Yes, there is one example by Omuri Sariku. In that example, the wave measure itself is invariant, and it has an infinite Laplace exponent. Yeah. And it has an infinite entropy. Yeah. Here, I don't know it's the same for this map, but anyway. So that's one example I know. Yeah, the necessity for it. So that's because entropy is not approximate here. I did it recently, but this result does not follow from the level 2 because the observable